that's the one I have to do. Okay, thank you all for coming. My name is Nicholas Crouch. I work here at Maths Learning Centre at the University of Adelaide. This is a revision seminar for Maths for Economists, the introductory one, they still call it that. We're going to cover a few topics. At the moment, we don't have anyone online, so I don't need to worry about that. Yeah, if you've got questions, please do ask me. One of the first things I'm going to do is pause and go, a lot of people, when they come to preparing for exams, sort of forget the key purpose, all right? The key purpose of the exam is to see if you've understood what we've told you, all right? And if we put it like that, then the first and possibly most important thing for preparing for an exam is knowing what we told you, all right? So answering the questions is actually a tool for help for us to decide if you understood what we told you. So being able to use what we've told you to answer those questions is the evidence we're using to say you do actually understand what we've done. And so the answering questions is not actually it is sort of the most important part, but it's actually secondary to what we're trying to do. We want you to demonstrate understanding, not get answers. Like none of these questions I couldn't do myself. So I'm not like trying to ask you to solve a difficult problem. What I want you to do is demonstrate understanding. So that means a couple of things, right? Firstly, really important to include your working. Secondly, if you don't know what to do, but you do know what the first thing you should do is, you should write that, all right? If you look at where you are and go, I don't know how that's going to work out, but I know I should do this first, let's just do that. And then sometimes once you've done that, you go, yeah, all right, if I was there, I'd do this, right? And so you can then, sometimes you can step your way all the way through a problem. I've done that numerous times myself, mostly from the point of view of, I will get one of these questions, and I'll go, I don't see how you're supposed to do that, but I would do this first. And then, it follows that this, and then this, and then, that's the answer. So it is possible to do these things. So I'm actually going to do a little bit of a recap of fractions. So the other thing I'm going to do is I keep a little list of okay. So all of the things I do here, so these notes that I'm writing and the recording will go up online sometime in the next sort of 48 hours, basically. David does all of that stuff. So it will happen. Okay. Like I said, when we were talking about possible topics, I'm going to talk about fractions just from the point of view that a good understanding of fractions is going to help us understand algebra better. All right. So for where we are, hopefully most of you feel reasonably confident with your algebra, but sort of going over these things is actually a really useful thing to do. All right. So all right. So adding fractions. If I have nice simple A on B plus C on D. All right. So we all remember the phrase create a common denominator. All right. So quite often they'll use the phrase lowest common denominator. And so what that means is we're going to try and make sure the denominator of both of my fractions have the same number in the bottom. So recap, numerator, top line, denominator, bottom line. So I can times by, we all know that I can times by 1, don't we? Oops. We also know that I'm dyslexic and I will write I will write things backwards. So I've taken this first fraction and I've times by d on d. Everybody's happy with that being 1, but it's going to change it to a denominator of b times d. And if I take my next one and I multiply by b on b, they now have the same denominator. These are so AD on BD plus CB on BD. Same denominator, so now I can add the numerators. All right. The other thing I'm going to point out, I've done this quite deliberately. When I have the product of two values together, all right, two of these variables together, or pronumerals, I've actually put them in alphabetical order. And this is actually a bit of a trick for doing algebra, right? Particularly when you've got multivariable functions, a thing that is the product of more than one pronumeral, if I put those in alphabetical order, it helps me identify when there's the same thing, all right? So addition and subtraction come under the same heading. So we're going to go. All right. So that's actually probably the one where I need to know the trick. All right. There's actual trick. All right. Create the common denominator. Then I can add the numerators. All right. So I do like to add in some comments just to make sure. So we're going to do something simple where I do A times A on B times C on D. All right. So multiplication is the easy one. Multiply numerators, multiply denominators. Right. And last one, division. And move it up. Yep. Well done. That is exactly what we need to be reminded of. All right. So all right. When we're dividing fractions, we multiply by the reciprocal. Okay. So if I have A on B divided by C on D, all right. Ideally, what I want is is brackets around these things. All right. So we're at the bit where we need to be careful about which bits are the fraction of what. All right, and I'll come to a little example in a minute. This is going to be, so I take my A on B and I multiply. Reciprocal means turn it upside down. So it's going to be D on C. And so it's actually not terribly hard to do, but I want to be careful. All right, hashtag warning. So said I needed to I want to be careful about putting brackets. Let's take the thing where I do A on B divided by C. All right. So let's assume this really is, as I said, A on B divided by C. Okay. Now, this should be, because it's A on B, that divided by C on 1. To write it as a fraction, and so that's going to be A on B times by 1 on C, A on BC. Let's try the other way of doing this though. Let's put the brackets on the bottom. So if I go A divided by B on C. All right, same plan. I'm going to write that as A on 1 divided by B divided by C. So it's going to be A on 1 times by C on B. All right. Notice that these are two different things, all right? So we want to get used to the idea that we're going to whack brackets around stuff if we're not sure, all right? And so the thing I originally said here was that it was A on B divided by C, so that should be that thing. And that's sometimes what you have to go back to. All right, what am I doing? Have I got that thing divided by this, or is it this divided by this fraction? And that's really important for working out what's going on here, okay? Now, what's going to happen is when we do derivatives of things, there are going to be messy things. I'm going to say messy things. Be very vague and go, messy stuff's going to happen. And so we're going to see doing these things in action. And you've probably been doing a lot of this, but it's good to go back, state the things we should know carefully, and then move on from there. Yeah? We're good? Moving on. All right. So, what was I going to do next? So, all right, log laws. So, go away and move this. Go away. That's what I want you to do. Sweet, that's the one. Log laws. So if we do log of A times B, it's going to be equal to log of A plus log of B. Log of A divided by B is equal to log of A minus log of B. And log of A to the power n. N comes out the front, log of A. Probably should get used to putting brackets around stuff like that. So those are my laws, right? That's the thing I'm going to base my understanding on. There is this thing that says, what does it say? It says log base A of x is equal to B is the same as saying A to the power of B is equal to x. So log is a way of getting the power. So the reason this comes out is because of this relationship, all right? So this is like the defining characteristic of log functions. Now, we're going to need to use this when it comes to doing sort of linear regressions and geometric progressions and sort of talking about payment schedules. So, so we might get into that, but if we think, now, so there was another thing. Notice here how I've put in the base. I've put in log base A. Give it a second. There you go. Log base A. And so this is the same base as the exponential function. All right. So they kind of match. So if I have an equation that was like 2 to the power x is equal to some number, then possibly using log base 2 would actually help. So if I was to take log base A of x, it's an interesting thing I can do. I can actually go, this would be ln of x divided by ln of A. Or possibly log base B of x over log base B of A. So there is actually a rule for change of base. I'm going to guess you guys being economics, finance types.
We look at this though, but that's worthwhile knowing.
So you do know that the log command on Excel, you can actually stipulate a base. All right, yeah. So there, I'm not sure if it's strictly speaking the same. There's there's usually about 3 log functions for most things. So log base 10, log base E, so ln, natural log. All right, you're okay with the, pause momentarily. You're okay with the use of natural log here? Yeah, cool. So you can, like my calculator has log base E or natural log and log base 10, but I could use that to get me a log to any other base following this sort of rule. All right. And specifically log base 2, like I say, Excel does actually have an option for log of a different base if you want. Worth knowing, but on ideally, you notice I didn't put a base for any of these rules. All right. When I come to these rules, I didn't actually put a base in because as long as I keep the base consistent through the rule, it doesn't matter. All right. It is always true regardless of which base we're using. All right. Possibly digress slightly and go, actually, if I talk about some of the exponential laws, so when I have sort of a to the power n times by a to the power m, that becomes a to the n plus n. So see how the product of two things, it's like the sum of the powers. It's the thing that's taking down the power. So if I have a to the power n to the power k, say, it's a to the power n times by k. And so 1 on a will be a to the minus 1. So 1 on a to the n, a to the minus n. Usually when we write out laws for exponents, we write in a couple more. So we sort of are explicitly stating these things. And that's sort of where, so this side is where this comes from. This is sort of, when it becomes dividing by, sort of puts it in the denominator. So there are a few things like a to the power 0 is always equal to 1. A to the power 1 is always equal to a. There is like, if I have an nth root, that will be equal to a to the 1 on. So to get a power get a fraction in the power, I'm taking a root, like a square root. So a square root would be a to the 1 on 2. And we're going to use that when it comes to doing differentiation. All right, and solving equations. So with, what do we normally see? We normally see something like 3e to the x is equal to, I'm going to say 10. Yep. There we go. So if we try doing this, what we're going to do is we're going to rearrange first. So we've got the e to the x part by itself. Needs to be by itself so that I can work out what it is. And then I'm going to do ln of both sides. Because this is base e, log is the natural log is the one that undoes e, so I'm going to use that one. If I really wanted to, I could write that as ln of 10 minus ln of 3. All right, kind of doesn't matter. I would probably, if I'm doing a calculator using Excel or whatever, I do it this way. And so this bit is going to tell me that x is equal to ln of 10 on 3. Right, there is a bit of a plan here, right? Sometimes I don't need to know the number. All right. So, but there's an option. No. I'm going to do that. And then I'm going to go, where is it? Where is it? Ah, there it is. Where'd it go? Did I close it? No, I didn't. Should be here. that one. There we go. All right. Favorite pastime. All right. So for this one here, equals ln. So you notice how Excel is telling me it's going to return the natural log of the number. And so I can just type it in as this. All right. Really, really simple. All right. And so it's going to give me a number. In actual fact, I'm going to say that. In actual fact, I wouldn't worry, like sometimes the number itself is not that important. All right. Leaving it as ln of 10 on 3 can actually be better sometimes. All right. Especially if I'm going to use it in another calculation. But also sometimes I just want a number. All right. So depends on context a little bit. So we're going to swap back. Sorry about messing around, but sweet. Go away. All right. So I can actually give an actual number. Okay. So what we're going to do is we're going to jump over and talk about geometric progressions and scheduled repayments. All right. So these things I'm going to use, but I thought it might be worth, and since you've mentioned it, it might be worth mentioning, sort of going over. Okay. All right. Geometric progression. Typically, geometric progression, I'd say, starts at A, so it's a sequence. A times A times R squared. So what I'm doing is A times R cubed. There should probably be two M's there. All right. We're going to point out quickly that I'm a maths lecturer, not an English major. There will be spelling mistakes. I'm also kind of dyslexic, and so I write things backwards from time to time. Well, actually, the worst one is I say things back. Like I say, if I see 12, I will sometimes say 21, and you're kind of going, how did that happen? I can, even in my brain, I'm saying 12, but the word come out 21. I'm like, mystical shit happens in my brain. So common ratio, what I really mean is if I was to sort of go, this is, so if I have some sort of sequence Bn, where this would be A times R to the N, then the ratio is a fancy word for saying fractions. Okay, so I'm going to have something like that. And so I can cancel out the A. So because it's a factor of the numerator and a factor of the denominator, I can cancel it out. It has to be a factor of the whole numerator and the whole denominator. All right. Now, this is going to leave me with, so this is like R times R times R, like N times, and this is like one more R. So that thing is going to cancel out with all but one of those. This number is going to be R. And so that's that common ratio. Now, what we really want
What BN?
BM is just a way of indexing. So I can sort of give, because I'm treating it as a sequence. All right. So the geometric regression is a sequence. All right. Now I'm going to distinguish between a sequence and a series. All right. So technically a series, so Sn would be sum from n is equal to 0, and maybe I should do I. I is equal to 0 to n of like my bi. All right. Summation I is equal to 0 to n of, and I'd go a times r to the power I. Okay. So the thing we're talking about, yes, that looks as, beg your pardon, what now?
So what's the
Oh, have you not seen this fancy, this thing here? It's fairly badly drawn. So it's the Greek letter sigma, and we use it for summation.
I don't know whether we touched on that.
so yeah, we
I've seen it in the data that I'm doing, but not in this math.
Didn't you? If you did, okay. There were choices about how you teach this, and there are some of these things where you go, I'm going to gloss over that little detail. This is like a shorthand. So this thing here would be going a plus a times r plus a times r squared plus dot 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 plus a r to the n. So it's a way of saying I'm going to sum up all of those things. So possibly, all right. So strictly speaking, you'd read that as the sum for all integers I from 0 to n. All right. And it's a similar sort of convention to how we do it with integrals. You know how we do the integral from a to b. The lower number is the from, and the upper number is where we go to. So we've sort of tried, there's a certain amount of trying to keep consistent over all the different sort of things we do with these things. And so it's a way of sort of going, where are we up to? So just a way of sort of working out what sort of things we got. So this is what we mean. Now, so the reason I've done this is there's a quaint little proof, right? So if I was to do a thing where I was to do Sn minus R times Sn, all right? So Sn would be this lot, A plus AR plus AR squared plus dot dot dot. And it goes up to AR to the n. All right. And then I'm going to take away AR. So I'm timesing all of these by R. So it's like AR squared plus AR cubed plus dot 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 plus the last one is going to be ARN plus 1. You can sort of see that this one's going to cancel with this one, and this one cancels with this one. This one will cancel with that one. What I'm left with is going to be A minus AR to the n plus 1. Over this side, this is Sn times 1, and this is minus R times Sn. So I can go Sn by 1 minus R. And so I can go Sn is equal to A minus AR to the n plus 1 on 1 minus R. Okay. See how, now this is a thing where I can factorize. So factorization, right? There should be a t-shirt that says factorization is your friend. And honestly, like factorization is that sort of friend who talks you up at a party, right? He's the one that goes, kind of, makes you look good in front of the girl you've been trying to impress. Right? Factorization does no wrong. He's like your greatest friend, man. So because there is an a here and an a here, I can go 1 minus r to the n plus 1. Or 1 minus r. Now, this is my formula for the sum of a geometric progression. All right. Your lecturer would have done this. Your lecturer probably should have done this for you. Good. Yeah, at least one of you is nodding, going, oh, yeah, I do remember that. We should pause momentarily, right? There is a certain amount of people feel like, oh, no, I didn't do the right thing. Right. At no point in my life do I think, really, you should have turned up to class. You should have paid more attention. I've been in the class. I've been that person who's gone, he said, what? And in some cases, I've been able to go back to the lecturer and listen through and go, oh, you did too, right? Because sometimes when you're in a class and you're being told a lot of new stuff, some of that gets lost. Some can be quite a lot. So if you're feeling a little bit overwhelmed by a course, you miss stuff. I'm going to say stuff again and again and again. And sometimes you just have to be in the right spot to hear it. All right.
I think when she went through how she got to that equation very quickly.
Yep.
So, but that wasn't the important bit. The equation was the important bit. That's why, some people might not remember the other bit.
So, when we come and talk about mortgage payments, all right. So, if we think about my mortgage payments, all right. Yeah, we're going to start with the standard process, all right. And the standard process is your first payment occurs at the end of the month. So, the best way to deal with any of these financial questions is actually draw a timeline. All right. All right. So, there's a horrible thing. All right. So now we know about compound interest. We kind of want to mention something about compound interest at this point in time. Yep. So if I have $1,000, so let's go. Unfortunately, if I freeform stuff, I have to go, oh, I need to talk about that before I can fill in the details. All right, compound interest. So quite often they'll say something like 6% per annum. So this is the yearly rate. All right. But what they do, if we say, what they're actually saying is they're going to give you a 12th of that as interest for each month. All right. So if you just sort of did a really rough thing and sort of go, oh, I did 12 lots of 6%, and 12 lots of 0.5%, that would be 6%. I'm going to call it a thing. Now, I might talk about effective interest rate somewhere else, but what this means is if I talk about, so there's things, future, oh, there's too many things. There are too many things. So future value. All right. And so that's going to be equal to your amount times by 1 plus, and I'm going to go my interest rate divided by 12 times by 1 times by 12 to the power of 1 times by 12. All right. 1 year, 12 months worth of compounding. All right. So when we do interest, I times by 1 plus interest rate as a fraction. Okay. This should probably, because this really should be percentage. All right. This is going to work out to be amount by 1 plus 0.06 on 12 to the power 12. All right. So each month I times by that factor. All right. And this is going to tell me how much this will be worth at the end of this period. That's why we call it a future value. So wonderful job about future value. Really, really simple. I'm going to go amount. And then I won't bother switching over to Excel for people to see what I'm doing. I'm just going to switch over so that I can do this. So I'm going to go equals brackets 1 plus, I'm going to use an extra bracket, 0.06 divided by 12, close off my brackets, to the power 12. Woohoo! Now, when I do this calculation, that number works out to be, let's go back to the picture. Where's Zoom? That should be Zoom. Why didn't you do that? Good. That should be 1.061 other numbers. I'm going to pause momentarily. These other numbers, all right, actually represent what's considered the effective interest rate. All right. So per annum interest rate and effective interest rate. So if I took my 6% compounded monthly, but treated as like was being added just once a year, this 0.61, whatever it was, let's actually just quickly check. Come on, there we go, 0.6168. 68, and then other decimal places. Actually, no, that looks like it's about right. Let's do this. Nope, other decimal places. This is like the effective interest rate. And so that's like, if I only added interest once a year, that would be what the interest rate would need to be equivalent of. All right. So it's a thing. So financial maths, if you're going to do financial maths, make sure you come and talk to me. Keep coming and talking to me. By the time you get to second or third year, less helpful. Definitely by the time you get to third year, but definitely first and second year can help. Yes.
Like the annual price rate or whatever.
Something like that. I'm always a little bit confused with the various different acronyms people use, because I teach financial maths from a mathematical point of view, not a finance point of view, which is kind of, but also can be quite useful. So yeah, so actually you guys wouldn't be doing financial maths, would you? Because you wouldn't, or do some of you hope to go down that path in the end? Not looking like it. Okay, sure. Yeah. So actual fact, the reason I'm doing this one is because, like, out of David and me, I'm the one who's done most economics. So most finance and economics, and this is where it occurs. So this is going to be the effective rate. Now, we were talking about mortgage payments. Mortgage payments are more or less the same thing, right? Except for they work the other way. All right. They kind of work backwards, not forwards. All right. And so what we've got to do is, like, if, let's say, for example, I want to borrow, I don't know, $50,000. I know 7 years sounds like a good number. And convenient. I'm going to use 6% because firstly, the calculation works out a bit nicer. Not that we're going to do it on the computer, but just nicer in terms of the thing. But also, All right, I want to know how it's compounded monthly. I could take my effective rate there. Now, I want to know how much that's going to cost me. All right. So, because the 50,000 is a present value, all right, that's what it's worth today. All right. So what I've got is I've got this thing where I get 50,000 right now. But then I have one payment and two payments and three payments and four payments. Now, the value, so this value has this thing has a future value. We could call that payment times by P times by 1 plus 0.06 on 12. And this one would be P by 1.0 plus 1.06 on 12 to the power 2, so on and so forth. Discounting. So that's going forward. That's giving me a future value. Its present value of that one. All right. Yeah, thank you. I was just looking at that going, yeah, that's not going to work, is it? So the present value of that first one is going to be the actual payment divided by like one lot of interest. All right. All right. This second one, when I discount it back to what it's worth now, all right, that one is going to get me that same payment, 1 plus 0.06 on 12, but it's got 2 months worth of discounting to be done. Okay. And so if I take this third one, same thing, payment 1 plus 0.06 on 12, power 3. 3 lots of discount. Pain in the ass, let me tell you. Okay. So
you're putting that formula is the payment you're going to
payment, yeah. We should say monthly payment. Okay. That's kind of really, really annoying, isn't it? So now I kind of know everything though, don't I? Except for what we're saying is what we've actually said is my 50,000 is equal to, I'm going to take the P is in all of them. And I'm going to go, I'm going to say let R equals 1 on 1 plus 0.06 on 12. So this would be R, and this would be R squared and R cubed.
now
Yeah, so R is like, it's not so much your interest rate, it's this is like, I would refer to it as a discount factor. Because it's something so when I say factor, it means I'm multiplying it by something. So I'm going to call it a discount factor. And this one, because I said 7 years, this should be 7 times 12, should be 84. All right. So there's a lot of annoying little things going on there. Now, I kind of got a formula for adding this stuff up. All right. So I'm kind of going, I always get to this point and go, have I done this the right way around? I'm gonna pretend I have, right? There is going to be you checking the formula. Actually, while I'm here. What am I doing? I've got the book. I want to just check how they've given you the annuity. Do you guys remember how they gave you the annuity formula? Cause so 200-ish.
I'm trying to remember how previous was you're working through to work out what the monthly repayment is, isn't it?
Yep.
And what we did, I think, was use a compound interest formula to work out what the future value was going to be, and then took the geometric series formula to work out what the repayments were going to be. You understand what I mean?
Yep. So what we, yeah, so what we're going to do is we're going to put a P, we're going to put an R, and we're going to go 1 plus R squared plus dot 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 plus R to the 83. Okay, so I can do that. And then I'm going to do a thing which is not going to be a lot of fun. I was like, part of what I've been doing is going, oh, I don't want to do it that way. So I've got a formula that says that sum should work out to be equal to, so P times R times pi, and then it should be 1 minus R to the n plus 1 on 1 minus R. All right. Now, I feel like every so often when you do these things, you go, yeah, I know, nobody's going to be happy with this plan. So I've got my P, because I'm timesing by R, I can just write this down in the bottom. So because this is n plus 1, and this would have been my n being 84, n plus 1, n 83, n would be 83, so n plus 1 would be 84. There's actually a little thing about, this is technically to the power 84 up here, but because it's 1, it makes no difference, so I'm not going to bother. And 1 minus 1 on 1 plus 0.06 on 12. All right. That looks terrible, doesn't it? Yep. No, maybe. We don't want to do that. Whoops, too high. Too high. Go, go, go. Come on. Oh, it's out of focus. I wonder if I can do much about that. No, I can't, because this thing is just going to take forever to do anything. Well, amusingly enough, better. All right. First thing I'm going to do, P on, so I'm going to write this as R plus 0.06 on R. Probably should have said when I take this 1 on, so that kind of, I can write that as 12 on 12 plus 0.06 on 12. Numbers. I want that to be a 12 and I want that to be a 12. Sure, that's going to work. All right. That's that bit. And then this bit here. All right. No, I wanted to finish writing this. This I can write as 1 on 12 plus 0.06 on 12. Oh, it's just out of screen. Jeez, I tell you. Do that thing. Now, this thing here, similar sort of pain. All right. So that should be like 1 plus 0.0606 on 12 minus 1 on 1 plus, oops. One plus 0.06 on 12 power 84. So that's my numerator. And my denominator is going to, I'm going to throw away that red pen. Red pens don't work for me. And this is going to be 1 plus 0.06 on 12 minus 1 on 1 plus 0.06 on 12. All right. Okay. Did someone say they wanted to do fractions? All right. So that sucks a lot, I hear you say. Yep. Where nobody's arguing with that particular assessment of the situation? No. Cool. So we're going to do a couple of things at this point in time. So you know how I said factorization is your friend, and he's like your best friend, do anything for you. Fractions are like that rich uncle, right? They'll help you out. They can get almost anything done. They're kind of annoying to have around. And so what you want to do is you want to use them and get rid of them as quickly as possible. All right. So here we have fractions. First thing we are going to try and do is get rid of the fractions. All right. And that means doing the operations that are here. So I've got a fraction divided by a fraction. Here I've got a number divided by a fraction. So I'm dividing by this fraction. So it's going to be P times by the reciprocal of this. 12 on 12 plus 0.06 as a number. That sucks, but that's okay. Did I do that the wrong way around? Yes, I did. Scratch that plan. Nobody saw that. Let's try again. Because this is R, this is like 1 on. All right, so I'm going to go P times by, because I'm doing the dividing by this thing. No, I'm timesing by that. That's why I did it that way. No, that's okay. We really are going to. Let's, R is this, because I'm timesing by R, this is 1 on, and I'm going to write it as 12 plus 0.06 on 12. This is going to be this fraction. So P times by the reciprocal, we're just putting in what R is. Because R is simplified down to thing you can't see on the page. This thing here, that's why I put in this. All right, that's what this bit is, just R. When I take this expression here, what I'm going to do is I'm going to write this as 1 plus 0.06 on not there, 12 power 84 minus 1. Now, so we've got horrible fraction inside fraction thing all over the place. It's terrible. So I'm dividing by this fraction. So I'm going to multiply by the reciprocal. So that's going to give me 1 plus 0.06 on 12 divided by, I've got a 1 and a 1. And so that's going to make my life easier. 0.06 on 12. Woohoo. Okay. So I kind of dismantled one fraction. This is going to take a little bit of doing, but it's going to suck. We have things to do, some of the algebra for us. I'm going to continue doing this because I can make it happen. I may stuff it up between here and there, but nobody's going to notice. Because we can do this, all right? So, because this is 1 divided by this, now notice how I've got brackets around it, so it's nice and clear what thing it is that I'm dividing by. I should be able to do this way. So this should be, so I should be able to do 12 on 12 plus 0.06. What am I going to do with this one? I am probably going to write this as 12 plus 0.06 on 12 power 84 minus 1. 12 plus 0.06 on 12, 84. Sure, 84. Sweet. Because I'm going to write that as 12 plus 0.06 on 12. All right, that thing. And then I'm dividing by this fraction, so I'm going to multiply by the reciprocal. 12 on 0.06. That sucks a lot.
Can I just ask what's all this equal to? Is it 50,000? Is that what it was?
Yep, that's where we started with. All right. Blur. I'm not loving this at all. All right. See this number and this thing? This 12 can cancel with that, and this can cancel with that because they're exactly the same thing. Sweet. Now, I put that and that together. And so I'm going to write this as 12 plus 0.06, 84. On 12 to the power 84. That might seem like a bad idea, but I'm dividing by this thing. And so this is going to be 12 to the 84. On 12 plus 0.06 to the 84. All right. No, we dropped off the bottom of the page. Right. Like this, but I'm gonna. There are better ways to do this, and I think I can expand this out, so I can do 12 plus 0.06 to 84 on 12 to the 84 times by this thing, times by 12 to the 84 on 12 plus 0.06 to the 84 minus 12 84 on 12 plus 0.06 84. You're going, this number works out to be 1. And I've got 12 on 0.06 times by 1 minus tiny little number. And so this thing here I'm going to write it like that because what did I say? What did I say R was? I said R was that is what that is. All right, it's a horrible thing. This is actually very close to the formula that you've got, actually. All right. So I can plug this in. At this point in time, you go, and yeah, I can see that look on the face. What we're supposed to, well, if you go back in the day, back when I was a lad, bank managers actually had a chart of a thing that said, basically you would look up the page that said term of loan, interest rate, find the appropriate value for this sum, take the amount that you were borrowing, divide it by that value, and it would work out what and it would give you your repayment value. All right. So it was all done by tables. All right. When computers came along, they put these formulas in, and they more or less did the same thing. Actually, they more or less gone, hey, I'll just put in the formula to calculate that number. So the formula for calculating the payment is always sucks. So because if we imagine, because we're doing the payment value, that's the hardest thing to calculate, if you like. I don't even know that I want to bother doing this because I think I've taken too long doing that particular thing. And I think it's going away from something that's useful. All right. All right. Do we want the number or do we want to let it go? Let it go. Sweet. Good. I'm down with the plan. I'm a huge fan of that, letting it go. Okay. All right. So I do want you to remember for financial math stuff, all right, compound interest formula, draw the timeline, all right? Are you asked about a present value or a future value? All right, present value, discount by interest rate. So basically divide by interest rate. Future value, increase, you multiply by interest factor, all right? And that will get you to your thing. Okay, that is going to get me there. So we are going to go and do a quick, where are we up to? All right. All right. All right. Differentiation. Okay, there is a formula. Okay, so that would be f dashed of x is equal to limit h goes to 0 of f of x plus h minus f of x on h. All right, I mention this because it is entirely possible that you could be asked to do differentiation by first principles. All right. So let f of x equal, I'm going to go x squared plus x. All right. Then f dashed of x is equal to limit h goes to 0, f of x plus h minus f of x on h. Let's interpret what that means in terms of the functions I'm given. So this should be, at one point, I'm going to take the limit. So it's important to sort of keep it in there, x plus h squared plus x plus h. All right. So when I'm doing, this is a composition of functions. I'm putting in x plus h where there's x. All right. So that's why I've said x plus h all squared is this term. X plus h is this term. And then minus x squared minus x. All on h. There's a little bit of expandy stuff. Limit. I'm going to do a trick you are allowed to do. You're allowed to go x plus h all squared. I know that is the first term squared plus the last term squared plus 2 times the first term times the last term. All right. You are allowed to do that. It is a genuine thing. Plus x plus h minus x squared minus x. All right. So rather than writing it all out, you can just go that squared plus that plus that times 2. Now I do some cancelling out thing. Minus x squared and plus x squared. Minus x and plus x. And what I'm left with, I should have on a h. limit h goes to 0. This is like h squared plus 2xh plus h. Okay. On h. All right. Catching up with our best friend, factorization. There's a h in each one of these terms. So I can go h by h squared plus h squared, h 2x plus 1. I need the 1 there because I want that h. So if I expand it out, h times h gives me h squared. H times 2x gives me 2xh. And h times 1 gets me h. On h. And now I can cancel it out, right? It's a factor of the whole numerator. And so that allows me to cancel it out. Let's write that out again. H goes to 0. And now it's just, so I've cancelled out the denominator. This is h plus 2x plus 1. And now I'm going to let h go to 0. So before, anywhere here, I'm dividing by h. I can't do that if h is 0. All right. Have you ever asked Siri what 0 divided by 0 is? All right. Fun thing to do if you happen to have an iPhone and want to kill time. I'm not sure if I'm going to assume it's still doing it, but yes. Anyway. But because I can now, so I dropped the bit where I let h go to 0, and I'm just going to let h go to 0. And so it's going to be 2x. This is my derivative. So this is a thing you will be asked to do. This is about the level of difficulty you would be asked to do in an exam. And if you wrote exactly that, you will get 4 marks. All right? Yes?
You have to write down.
You know what? So I have an ex-wife who is is an ex-wife. I've got lots of things to say about her. One of the things she taught me, though, was that it doesn't take very long to write these steps. All right? What actually takes time is when you sit and try and do it in your head. All right? Took me 30 seconds, right? Took me no time at all to write it. And so I just did the algebra. That thing, do that, did lots of small steps in very little time. All right? Takes longer to do fewer steps, actually. And if you just commit to doing them and do them as they're written, getting them right. Firstly, you're going to make fewer mistakes. And secondly, you're going to get through quicker. All right. So I'm actually a big fan of doing small steps quickly. All right. Reduces the number of mistakes, gets you through quicker. All right. Because you're holding less in your brain. All right. Like, strictly speaking, this is completely correct. Every time I've written this, limit, because I need that there to justify why I'm dividing by something that's going to go to 0. Even here, when I've then cancelled them out, it's only at that point that I can actually go, actually take the limit as h goes to 0. So that's where I basically set h is equal to 0. So there is one could argue if I needed to do that exactly, but I wanted to be clear about the steps. And it wouldn't be wrong. All right. The key part, not wrong. Too many steps, not a problem. Not enough steps and getting it wrong, problem. All right. So it's really important. So the moral of the story is, firstly, you can learn something from your ex-wife, regardless of how much you don't like her. And secondly, do small steps quickly. All right. Doing small steps quickly saves you time. Okay. So that's the first thing about differentiation. So there is like 2 major, this is a very small thing that they may ask you to do with differentiation. All right. And it's important that we recognize the phrase from first principles, because that's the thing that tells us this is what we are supposed to do. Differentiate without that phrase by first principles, you're going to do something else. Let's talk about the rules of differentiation. So you have been told, so let's see. So you have been told the derivative with respect to x of x to the power n times by the power, take 1 from the power. All right, that's the rule. derivative with respect to x, there is a special case. No, wrong one. D by dx of ln of x is equal to 1 on x. All right. You do log functions, so you need to know about log functions. D by dx of e to the x is equal to e to the x. All right. So this one covers most polynomial things, log things, exponential things. Now, there's special cases. Derivative with respect to x of log base a of x is equal to, which one is it? Should be, so this is kind of like the three classes of functions you deal with, all right? Polynomial type functions, log type functions, exponential type functions. All right. You then get told that the derivative with respect to x of some constant times f of x is equal to constant times the derivative with respect to x of f of x. All right. Basically, if I had 7x to the power 3, I could just put the 7 out the front. Make my life easy. All right. Derivative with respect to x of f of x plus g of x is equal to derivative with respect to x of f of x plus derivative with respect to x of g of x. And so addition rule, I can break, if I've got sum of functions, I can break it up into sum of derivatives. Woohoo, everybody happy. And so now we come to special one. Product rule, derivative with respect to x of f of x times g of x is equal to f of x times by the derivative with respect to x of g of x plus derivative with respect to x of f of x. I'm going to whack brackets around that so I can count by g of x. All right. Okay. They are painful. So these two are rules that we can just apply anywhere. This is a special rule. When I have the product of functions, I have to use product rule. Pain in the bum, let me tell you. But it gets worse. All right. So, quotient rule. Derivative with respect to x of f of x on g of x. At this point in time, I'm going to go, we know about dash notation, don't we? We go f derivative of the top line times the bottom line minus top line times the derivative of the bottom line. And all on bottom line squared. Okay. Sweet. Now, first thing to remember, looks a lot like, I could write this as f times g dashed plus f dashed g that way. Looks a bit like the product rule, but there's a minus sign. And the minus sign actually travels with the derivative of the bottom line. Okay? That's kind of the thing that tells us what we're supposed to do. Now, there is another one. All right. So in actual fact, derivatives are the things that make us understand functions better. Or the reasons we need to understand functions better. So if I go derivative with respect to of f composed with g of x, this is where I go derivative of f composed with g of x times by g dashed of x. Or how we say this one. So my dad was a maths teacher. I know, hard to believe, but so whenever I talked about chain rule, my dad would go derivative of the outer function composed with the inner function times by the derivative of the inner function. All right. And unfortunately, one of the things that does is it makes you remember it forever. Forever. I'm pretty sure I'm going to have dementia and I'm going to be able to tell you that. I do have dreams of me sort of, having dementia and helping people with their first two mouths, but not being able to remember where I live. Yeah, it's kind of, I've done so much of this. These are the rules we want to use. All right. So what are we going to be asked to do with them? All right. So I'm going to go through some simple ones. So if I go derivative with respect to x of, say, 2x squared plus 3x plus 7, right, because of my rules above, I could, if I really wanted to, I could write this is 2 times the derivative of x squared with respect to x plus 3 times the derivative of x with respect to x plus 7 times the derivative of 1 with respect to x. I could do that, all right? We don't do that because we kind of know these rules and we just kind of apply them. But I could. So this would be 2 times 2x, using my rule, plus 3. This is x to the power 1, so times by the power, divide, take 1 from the power. X to the power 0 would be just 1. So this is just 3 times 1, if you like, plus, and that's going to be 0. So 4x plus 3. All right, you kind of all knew that already, right? Kind of already knew that. Now, I'm not going to be able to happen. So let's do this. So if I want to differentiate with respect to x, if I keep it simple, I'm going x to the 7 times e to the x. All right, this is product rule. So under the heading of do things in small steps, being clear about what you did, I could go, well, f of x is just x to the 7, and g of x is just e to the x. Derivative of x, so f dash is just going to be 7x to the power 6. G dash is equal to e to the x. So need to say this, derivative of an exponential function is its own derivative, all right? Even when it wasn't base e, it was itself times by a number, all right? That number was ln of a, but it's whenever I do the derivative of an exponential function, I get the exponential function back, possibly times by something, okay? Really important, all right? And I'm just going to put it together. The rule says f dash times g, so that one. So x to the 7 times e to the x plus this one, 7x to the power 6, e to the x. If I want to, I've got an e to the x on each one of these too. So I could put the e to the x out the front and go x to the 7 plus 7x to the power 6. If I wanted to get even fussier with this, this is x to the 6. This is just x to the 6 times x. So I can go e to the x times x to the power 6, and then x plus 7. I could do that, all right? This is more factorization, all right?
Is the top one defined?
Yes. You could possibly have got away with that. This says I know what I'm doing. This says I'm showing off. All right. So know what I'm doing things, good idea. Showing off, possibly leave it for another time. All right. We are not circuit performers. We don't need a good review at the end of this. We just need to get the right answer. However, because one of the things we're going to do with derivatives is go, it's equal to 0 at this point. This form here is going to allow me to go, well, it could be equal to 0 when that's equal to 0, or when that's equal to 0, or when that's equal to 0. And that narrows down what I have to do a lot more, all right? So hashtag e to the x is never equal to 0. All right, need to say this a few more times, but just e to the x is never equal to 0. So part of this factorization is me going, hey, but that bit's never equal to 0. All right. I only have to worry about this polynomial part. So, got my thing. Now, I don't know, what's a good thing to do? I know what to do. So if I go derivative with respect to x of, I'm going to again keep it relatively simple, but use the things I've already used. So my f of x is equal to x to the 6, my g of x is equal to ln of x, and so f dashed is equal to 6x to the 5, g dashed, refer to the table, derivative of ln of x, 1 on x. All right, and so my derivative with respect to x of x to the 6 on ln of x is going to be equal to, oh, yep, yes. I was doing all right there for a little bit. Derivative of the top line times the bottom line, so 6x to the 5 times ln of x minus the derivative of the bottom line, 1 on x, times the top line, x to the 6, all on ln of x squared. Now, I am going to just simplify this thing a little bit to go 6x to the 5 ln of x. This, I'm going to, so when it's something like this, where it's like 1 on x times by x to the 6, I really should go to the trouble of going, that's x to the 5. All right? Should go to the trouble of. I'm going to leave the denominator it is. There is actually nothing I can do with that denominator. I'm going to let it go. All right? The other thing I might do, so again, because I'm thinking about this as something I might want to work out where it's equal to 0, doing that factorization is going to allow me to go, hey, if this thing was equal to 0, this bit's equal to 0, or this bit's equal to 0. So if a fraction is equal to 0, the numerator has got to be equal to 0. Possibly for this question, probably should have done x not equal to 1. Because if x was equal to 1, this thing would not be defined. And I cannot have a value for a derivative where the function is not defined. All right? And actually, yeah, because it goes to 0, the behavior of the derivative is terrible around that particular area, around that point. There's a discontinuity in the function, and there's a discontinuity in the derivative. So, so this is all sort of, you know, x not equal to 1. All right. And it's worth remembering that. That can be a trap. Most lecturers don't do that. And I don't know your lecturer, but I'm sort of pretty confident if they're lecturing this course, they won't be doing that to you. Okay? So
what time is log to the base e of x can never be 1 when you've got log to the base e of x.
Yep. Well, log base anything of 1 is 0. All right?
Yeah, fair enough.
And so that's why,
Yep.
and have to avoid the divide by 0 thing. All right? It's not something that I would never put that in this subject particularly as an exam. I might put it as a tutorial or discussion question, but I wouldn't put it in the exam because that's not the sort of thing that we're going to do. Yes.
You just take 20 seconds to explain how minus half x times
This is not half. This is 1 on x times x to the 6. All right, so if we do this off to the side, so if I do 1 on x times by x to the 6, I'm multiplying fractions technically, so it's x to the 6 on x. If we think about that, I can write that as x times x to the 5 on x. And so that allows me to cancel it out. Because x to the 6 is just x times x times x times x times x times x, right? And so I can cancel one of those out, all right? And that is something that you would be expected to notice, all right? If I saw that, I would be going, ooh, didn't finish it for some reason. And so so from there to there, I would expect. From there to there, Not necessarily. All right. If I'm asking you to work out where a stationary point, where this is equal to 0, I would expect you to do that. All right.
Finding that even with this example, so
Okay. So I'm gonna let d on dx equal 0, and so therefore x to the 5 6 ln of x minus 1. No. Oh yeah, no, I want that. Can I write that again? X to the 5 6 ln of x minus 1 all on ln of x squared equal to 0. And so I'm going to go x to the 5 6 ln of x minus 1. Don't want that bracket there. Keep on doing that. Is equal to 0. No, just greater than 2. All right. All right. Other thing. Greater than 0. Keep on wanting to say greater than or equal to, greater than 0. ln of x got to be greater. And so because natural log is only defined for x greater than 0, this has a natural log in it, I've got to have my x greater than 0. And because I'm dividing by it, I have to exclude 1. That means this. So ordinarily, so x not equal to 0. All right, this normally would tell me that x is equal to 0. But I have to exclude 0 from my range. This is actually kind of a fun thing. All right, so we have to exclude that particular thing from it. But then I'm going, okay, this bit. So I can't have x to the 6 equal to 0, so I need 6 ln of x minus 1 is equal to 0. Or 6 ln of x equal to 1, which is ln of x is equal to 1 on 6. So x is equal to, e to the 1 on 6. Whatever that number is. E to the 1 on 6. Let's go to the calculator. All right. Now, I'm not sure if you guys know about the trick for the exponential function. E to the x divided by 6. That number is equal to 1.1814 ... numbers. All right. It's a thing. And let's go.
when it ln x to the power of 2, next step the denominator not there.
Oh, so right. There is a fancy rule. Right. So if I have a fraction, if I have a on b equal to 0, that tells me that a equals 0, and also b is not equal to 0. All right? Yeah. So anytime you have a fraction that's equal to 0, the numerator is 0. All right? The denominator is not 0. You can just, so anytime you're making a fraction equal to 0, just the numerator equals 0. You kind of want to check that the denominator is not equal to 0 at any of those points as well, because then you would have 0 divided by 0 and refer to what Siri tells you. And if not, Google what Siri says when you ask 0 divided by 0, because I'm sure if it doesn't actually come up if you've got an iPhone, then someone will have definitely put it down. So, okay, so yes, that's how you go about showing this is equal to 0. And that factorization is that process. So the reason I wrote it as product of factors, this one equal to 0 or this one is equal to 0. There's actually a thing called the null factor theorem. They talk about it in year 12, where you go, if A times B equals 0, A equals 0 or B equals 0 or both. All right. So if I know that the product of two things is equal to 0, at least one of them is 0. All right. That's one of the joys about numbers. All right. There is a whole lot of, you know, how do I break if I times two things together and get 0, can I do it with non-zero things? And the answer is a different branch of mathematics, which doesn't deal with actual numbers. It deals with sort of things. Now, where was I up to? 8, 9. Okay, so we're getting there. So we've done that. All right. So what can we do? Okay, what's fun? What's fun? So what I wanted to do, right, I'm going to try this. All right, I'm going to go f of x is equal to, and I'm going to go x squared minus x e to the x squared. Okay? All right. Okay, so this is where my plan of being a little bit uptight about going F's and G's and stuff can actually starts to make a bit of sense. All right. So I'm going to call this G1 and G2. All right. So G1 is equal to x squared minus x, and G2 is equal to e to the x squared. All right. G1 dashed, nice and easy, is equal to 2x minus 1. Love the plan. G2 dashed. Oh, do you remember our chain rule? All right. This is like e to the f of x times f dashed of x sort of thing. So in this case, it's going to be e to the x squared times by the derivative of that power. So 2x. Okay. So this, if this thing on e to the x is not x, I have to remember to times by the derivative of it. If it's 2x, I have to still remember to times by the derivative of it, even though that number is just going to be 2. If it's not strictly x, it makes it a composition of functions. Technically, I'm applying chain rule, and so that means for e to the x times by the derivative of it. I'm gonna do some things in a second, but let's do this trick. Yeah, loving the plan. Okay, so putting it together, f dashed of x. So first one, derivative of the first one times the second one. Right, derivative of the first one, 2x minus 1 times the second one, e to the x squared, plus first one, x squared minus x, times the derivative of the second one, e to the x squared times 2x. All right. Conveniently, I've got e to the x squared. E to the x squared can sit there. And then what I've got is I've got a 2x plus 2x minus 1 here, plus 2x times by x squared minus x. Blur. Nobody is loving that plan. E to the x squared by, so this is 2x minus 1 minus 2x cubed, no, plus 2x cubed, minus 2x squared. All right, e to the x squared, and then 2x cubed minus 2x squared plus 2x. Notice there's no sign in front of it, so that is technically a plus. All right, minus 1. Do you ever look at something and go, perhaps I made a mistake? So I knew that I did something, so I knew it would be interesting. I've kind of done a thing where I've gone, oh, that's what we might refer to as too interesting. So I'm going to cheat. All right. So this particular thing, where that one? Well done. So Wolfram, so I get really grumpy at people who use things to work out what these values are. Whoa, that's a horrible number. All right, sure. Did it give it to me in third form? No, it didn't. Sure. All right. So all right. So this is a really good example of why you don't make stuff up before you write an exam. Because I was like, oh, I want to make sure there's a turning point in here. But also then we've gone, ooh, that's not going to work very nicely. What I'm going to do is I'm going to just save us a bit of time and go, what did I say? X power 2 minus x times x power 2. All right. If I do this, all right, sweet. Okay. Yeah, you can see that. So this is like a dodgy way of getting a graph of it nice and quickly. There are other things like a thing called Desmos or GeoGebra that do graphs. I wanted Wolfram just to tell me the root. All right. So e to the x squared yep, good point. There we go. All right. So when we get to this point, I'm going this bit always greater than 0. 2x cubed minus 2x squared plus 2x minus 1 equal to 0. That tells me that x is equal to 0 0.6478 other numbers. All right. Okay, now I don't want to do this. But so what I would do at this point in time is go, okay, what do these things look like? All right. Now, if I'd done this properly, all right, there would be two options. Actually, I can do this. Sign diagram. All right. Because there's only one turning point, I can do this by going, let's pick, this number is sort of a little bit more than a half. So if I chose x to be a half, this would be a quarter minus a half. So that would be a negative times a positive number. So this is my 0.64 ... And so here, sorry, which one? Here, sorry. No, this thing. Nobody's loving that. Just a second. I would have to go 2 on 8 minus 2 on 4 plus 2 on 2 minus 1. That's going to cancel each other out. That is still going to be negative. Beautiful. And I am just going to assume it's going to be positive if I go the other side. All right. So I'm only looking at the sign of these factors. All right. I've done enough to go, it's going to be positive. It's going to be, so actually I could have put in 0. So if I used x is equal to 0, because that's on this side, I'd go 0 plus 0 plus 0 minus 1, negative. Woohoo. I could do that. All right. There's only one turn. I've only got one turning point. I need just something on the left of it and then something on the right of it. And so I could take number 1. And if I took 1, this would be 2 and this would be minus 2. So that would be 0. And this would be 2 minus 1 and it would be 1 and it would be positive. So now I've got this thing where my slope comes in negative and goes out positive. And so therefore, f of x equal to x squared minus x e to the x squared has a other numbers. Okay, so that's what I do. So I sign diagram. There is a secret sort of extra option. There's a thing called the second derivative test. I didn't actually see it in your notes when I thumb through, but it used to be in the notes. Did we talk about second derivative test at all? All right, second derivative test is literally, I take the second derivative and I work out the value, the sign of the second derivative at the point rather than either side of the point. All right, can be better, can be worse. This one, going to be quite honest with you, a lot worse. The second derivative of that function would be unpleasant. Okay, sure.
Fine. So the derivative of e to the x squared, 2x e to the x squared.
Yes. So you're getting the function back, but times by the derivative of that power. All right. So with exponential functions, always get the exponential function back exactly as it was written, times by something else. Okay. Always. All right. Sweet. I forgot to do this. Where was I up to? 9, 10, 9. Okay, sure. Now, so that would be how I'd go about doing maximum and minimum. Let's see if we can do something that is even less fun. What do we see as less fun, do we think? So, all right. Okay. So what I'd really like to do is I'd try and like to do a multivariable function. So a two-variable function. So I want an f of x, y. And I am trying to think of something that is not too bad, but is going to be fun to do. Well, illustrative rather than, actually what I want to do, I'm going to do e to the x times y plus x squared minus y cubed. Okay, so hashtag, I have no idea what's going to happen. All right. So if I'm asked to find maximum minimums, strictly speaking, I probably should say local here, local maximum and minimum, because I'm not finding the quote unquote global extrema. All right. This is completely reasonable for an exam question, except for the numbers might turn out terrible. All right. Because I haven't thought about this at all. I've just gone, hey, let's do that. It may work out great and it may work out terrible. All right. But the process is going to be the same. You find the partial derivative with respect to x. So partial derivative with respect to x, I differentiate x as if it's a variable. I'm treating y as if it's a fixed number. All right. So when I come down to do this, e to the xy, I get the exponential function back. I've got a times by the derivative of that power, but I'm treating x as a variable and y as a constant. So if it was 7x, then I would be timesing by 7. Because it's yx, I'm going to times by y, the derivative of this power with respect to x, holding y constant. All right. So some of these things can help if you just sort of go through what you're doing. I'm differentiating with respect to x while holding y as a constant. Okay, yes, I'm running out of time. I'm going to try and do this as quickly as possible. 2x. When I differentiate y, because this is just like, so if y was 7, this would be 347, 43. Differentiate that number, it's 0. So I don't even need to put it in. And so I'd want to work out where that's equal to 0. Nobody's loving that. df dy is equal to e to the xy. And so same sort of rule, but I'm differentiating with respect to y. So differentiating with respect to y, holding x constant, that means this value is x minus y cubed is equal to 0. All right, you know how I said I wouldn't do this to you without checking it first? There is a reason for this, all right? That look on your face, yes, that is. Oh, nope, I should have done that. Well done, yes. It really should have been minus 3y squared. So, I'm actually going to do something you possibly wouldn't normally do. Plus 3y squared. And so I'm going to have e to the xy is equal to so pros and cons with this plan. All right. So I'm about to do a thing which I do not recommend. All right. Because I'm going to say I'm going to make that thing equal. So make those two things equal. This will not guarantee that I get 0. It will just make those two things equal. All right. And so I've got to check. All right. I may end up doing some dodgy stuff. And so I'm going to have to go back. I might. So it means so this is not the go-to strategy. But also you won't get this in the exam. So I'm just going to. And so that means I'm going to get 2x squared minus 2x squared is equal to 3y cubed. All right, so x squared is equal to 3 on 2 minus 3 on 2y cubed. Put up a little bit. All right. So there will be a number. There will be a number. This is going to get me a whole line of numbers, isn't it? Okay. What's actually going to happen? Y squared, x cubed. So I'm going to have x is equal to plus or minus square root of 3y squared cubed on 2. All right. Wonder if I can do that. No, not going to happen. All right, I'm going to let this go. All right. This is not what you were going to get. So let's try and go. What could you get? Normally what will happen is I will get like something like e to the x by 2x plus y equal to 0, and e to the y is equal to, I don't know, minus y plus x is equal to 0. All right. If we've done it correctly, we'll get something like that. All right. All right. All right. This is where I go, those bits can't be equal to 0. So I have to go 2x plus y is equal to 0 and minus y plus x is equal to 0. And so therefore I'm going to get like 3x is equal to 0. Move it up a bit. Yep. And that's x is equal to 0. And so therefore y is equal to 0. So I'd only get a single point. All right. Normally when we do something like that, that is what's going to happen. Unfortunately, making up examples to try and make it non-trivial made it too hard. So that's the thing. Possibly, if you've just got about 2 minutes, I'll try and just go through Lagrange multipliers. All right. So Lagrange multipliers. Do you have time or not? No, that's okay. You go. The recording will be up. I will put it up and I will just talk through an example of how to do Lagrange multipliers. No worries. Okay, fine.
Yeah, a little bit.
Yep, sure. I'm just trying to, yeah, sorry. That's restricted to what can we do? Okay. All right. So the plan is form the Lagrangian. All right. So that's where we go. L is equal to f of x minus lambda times g of x. All right. Where g of x equals 0 is the constraint. So in this case, that would be x cubed plus 3xy squared plus y squared minus lambda. I need this to be equal to 0. So I can do this in one of two ways. All right. So I can do y minus x squared. And I think I'm just going to do that. I could put it the other way around. It would make no difference. Okay. And so all right, so we're going to do the derivative of the Lagrangian with respect to x, which is going to be 3x squared plus 3y squared plus 2 lambda x. And I'm going to make that equal to 0. That with respect to y is going to be equal to 6xy plus 2y squared minus lambda is equal to 0. And then technically I've got to do the Lagrangian with respect to lambda. And that is just going to get me y minus x squared is equal to 0. All right. So what we've done is we've introduced this lambda, and this lambda is going to help me connect these two things. All right. So I'm actually going to use this one to say lambda is equal to 6xy plus 2y squared. And so then I'm going to put it into here, and I'm going to have 3x squared plus 3y squared plus 2 times x times 6xy plus 2y squared. And so 3x squared plus 3y squared plus 12x squared y plus 4xy squared. Blah. Okay. Yeah. Okay. All right. All right. We are trying to do this in non-trivial time, so we are going to go and do this. All right. If nothing else, we should teach you how to use Wolfram Alpha. 3 times x to the power 2 plus 3y power 2 plus 12x power 2y plus 4x y power 2 equals 0. All right. Okay, if in doubt, check that out. Well, hey, Check it out. I wonder if that's true. Oh, of course. Well, 0, 0 is a solution. This thing is saying that -3 on 4 is a solution. Sorry, 3 on 4 and 3 on 16.
What back do you shoot?
I'm going to write these down before I get there. -9 and 27. Okay, so let's go back to here. There we go. So these are saying I've got 3 points. Yes. Sorry. Oh, did I type it in wrong? Let's go back. Let's quickly check. Oh, I did put a cubed in there when I meant a squared. Let's see if that's going to make my life better. I'm going to go with no. Did I get that right? That's right. Yep. Okay. And see how actually it's interesting to see what it's done here, where it's given the x value as a function of y using the quadratic formula. And it's got some, it's actually giving you the region. And actually what it's saying is there is no points. So interestingly enough, for this particular curve, what I've done is I've found a path that has no turning points. Like I said, people don't actually realize how hard it is to write an exam question. See, it didn't look that bad, did it? It looked kind of good. I thought I was onto a winner, to be quite honest. But I was clearly wrong. The process is right. So you see how I've gone, oh, I can get lambda from this expression. Whoops, sorry. All right, so I've got my first order conditions. I can get lambda from here, all right? And then actually I could have done a thing once I've got this expression. I could have done one more thing. Because I can replace x squared by y, I could have gone like 3y plus 3y squared plus 12, and that's going to be y squared plus, that sucks, poo. 4, and that's square root of y squared. Oh, does actually tell me, does tell me that I get 0, 0 as a solution if I do that. Yes. Yes. Just because it's unfortunate in that it's got sort of, yeah, there is not an easy way to do that, and possibly other things. All right, there is a turning point. There is a point, 0, 0. Then I actually have to look. So Lagrange multipliers tells you where the critical point is of that function along that path. All right. So to sort of put it into context, what we did is we created a path. We sort of said this path. All right. And so if you imagine the function defines a road through it defines the hills, and this defines the road through the hills. All right. What we're doing is we're working out where along the road is it actually flat. All right. So we're driving. So what we're going to do is we're going to stretch out that road so it's a straight line, and we can look along it and see the points where it's flat. So it'll tell us maximums, minimums. It'll even technically tell us points of inflection. All right.
Like when the equation identify when you're supposed to use it, if that makes sense.
Sorry.
So when you identify,
Oh, so Lagrange multipliers is what we call constrained optimization. So when there's a restriction on my function, so there's two types. There's with constraint optimization falls into sort of two buckets, one of which is called linear. And I'm not sure if you talked about a thing called simplex algorithm at all. Going to go with no. They did actually use, at one stage they did try and put it in the course, but honestly, there is too much in the course from what you're expected to know. So if you come in with their expected knowledge, then the answer is you couldn't get through that much. All right. If you've kept up to here, well done. So there's linear constraint optimization and then just sort of ordinary constraint optimization. And so what you're doing is, this is just constraint optimization, all right? And so the only technique you have for this at this point in time is this Lagrange multipliers approach. So if it says subject to or something, or constrained by, then that's telling you there is a constraint to your domain. And so that tells you you have to do Lagrange multipliers.
Question like undetermined, and in that sense,
Like the thing I started with is actually very much like an exam question. All right. So find the maximum of this function restricted to. All right. Yeah, restricted to given the constraint of whatever. So they're all, there's different ways of saying it. Look at your assignments and the examples you did, because that's actually going to be the language that's likely to be used by your lecturer. So particularly anywhere where your lecturer has actually done an example, that's where you listen carefully for the words they've used to describe that constraint, because that's how they're going to talk about it, and so that's how it's likely to be described.
Constrained and unconstrained.
Yeah. So if there's no constraint mentioned, do the derivative. So multivariable functions, both derivatives got to be equal to 0. Single variable function, there is only one derivative to consider. It's got to be equal to 0. So a way to say it is just all derivatives must be equal to 0, and that will get you your answer. Okay.
Thank you.
I think we're out of time.
Yeah.
But thank you for coming. Thank you for your questions. Made it a lot more interesting for me and everybody at home. I am going to stop sharing. And where's the bit that says recording? Where's the recording thing? Where's the recording thing? Ah, recording. There, that one. Yeah, are you sure you want to stop the